How do we start this?
Maybe writing the element itself.
Okay, which elements?
You meant to say elements.
I completely agree with elements, so let's stick with elements.
Okay.
Which element should we start with?
Sodium.
Yep. So what is the symbol for sodium? And you mentioned hydride. What is our symbol for hydride?
OH.
Does everybody want to agree with him? Hydride is OH. It's just H.
Oh,
what is OH?
I'm thinking hydroxide. I'm sorry.
It's hydroxide. It's okay. NaH. This also says solid. Where do we specify the solid? After the sodium? After the name of our compound, sodium hydride. So we've got our first three words translated. What does reacts with mean? Plus. Okay, and now we're going to backtrack because I messed up. What is the charge on sodium? A +1. And since you said it in kind of a question, how do we know it's a +1? It's in the first column. So you're required to memorize the charges of all the elements in the first and second columns, and then zinc, cadmium, silver for the metals, and then nitrogen, oxygen, fluorine, the stuff underneath them. Okay? So you should have those memorized so that when I ask for the charge, you know it. Okay? And the reason why we need to know that is that we have to make sure that this formula that we've written is correct. What is the charge on hydride? That is admittedly a much more difficult one. It's a -1. Hydride's kind of a weird, tricky thing. We won't stress a whole lot about it. We won't see it a whole lot except for probably right here. Okay, so it's a -1. Is that formula correct? Yes? Why is it correct? The charges balance out. We have a proper formula. So yes, that formula is correct. Okay, reacts with, what's the next thing? Acetic acid. So when we see that, what does that mean for us for what we should be translating for our symbols? Okay, so we get a couple things going on here. So I see people actively trying to figure this out and look at the periodic table. That's pretty awesome. Unfortunately, the periodic table is not going to help you. And I see other people just staring off into nothingness, which maybe you're trying to pull up some mental library, okay, or you're completely lost. It's okay. Acid. What does it mean to be an acid? It needs to be aqueous. So we know the phase. What else does it need to be? That's kind of a hint. If we look at the products, sorry, I'm going to talk over you for a second. We also have aqueous sodium acetate. That one is not named an acid, it's still aqueous. So aqueous does not make it an acid. Okay? I need it to be aqueous and I need a hydrogen. Okay? I need a hydrogen placed in front. Okay? So that's what it means to be the acid. Okay? And ultimately that part is the ic acid. So what is this acetate part? We could try and go arsenate, and that's where I think at least James was going when he's looking at the periodic table. And I said the periodic table does not help us in this case. Okay, if it was arsenic, we'd be looking at a binary acid. The name would be hydroarsenic acid. Doesn't say hydro, which means it's not a binary acid. It means it's ternary acid. The hydrogen immediately gets put in there. The rest of the name of the acid is based off of the complex ion that makes it up. Okay? The ic comes from, when do you get sick? When you ate too much. So what we're looking at is acetate The acetate ion is C2H3O2. How do you know that's the acetate ion? You're supposed to memorize it. That's one of the ones that you need to memorize. If you don't have it memorized, you can't answer the question. Okay? Some ions you're required to memorize, some of them you aren't. This is one you are. What is the charge on the acetate ion? A -1. What is the charge on the hydrogen ion? It's a +1. Why is it not -1?
Because otherwise it wouldn't cancel out the charge.
No, unfortunately not. Didn't I say -1 right here for that H?
Oh, you said hydrogen's
Hydrogen's a little weird. How do we know the green hydrogen is not the blue hydrogen as far as the charge?
Because it's
listed it out.
Okay. Very few clues are going to help you with this. One clue, one's in blue, one's in green. I color-coded them intentionally to represent their different charges. Okay. The name of them also gives us a hint as to the charge. The green one is a hydrogen ion. The blue one is hydride. If you look up to the nomenclature of it, it's a hydride. When does the "ide" ending come in? When is that "ide" suffix used? When it's an anion. You only use the "ide" ending when it's an anion. So looking at the name gives us a hint that we're looking at the negatively charged hydrogen. Okay? And that's why we know the blue one is -1, and the green one ends up coming in as a +1. Hydrogen is typically a +1. That's why it's found in that column. Yes, it's weird. Sometimes you'll see hydrogen on both sides of the periodic table. Immediately next to helium, right above fluorine, which is important because what is the charge for fluorine? A -1 charge. Right? So that's why it can pop back and forth depending on its charge state. Okay? To produce. Okay, we could go with an equals. Chemistry doesn't like equals. It's an arrow, a reaction arrow. And because I drew this horribly spaced, we're going to draw the reaction arrow underneath. Okay? To produce what?
Aqueous sodium acetate.
Aqueous sodium acetate. So what could we use? What could we write? We could write the AQ. Where does the AQ typically show up? At the end. So that gets a little bit tricky to kind of fold in there, but we could try and sneak that in at the end. What goes in front of it? Na for the sodium.
And then
The acetate, what is the acetate? C2H3O2. What's the charge on acetate? A -1. The charge on sodium? +1. Is that formula correct?
yes.
Yes, the charges balance out. Okay, and what does and mean?
Plus.
A plus. And what?
Hydrogen gas.
Hydrogen gas. What is our symbol for hydrogen gas?
So
Hydrogen is H. What is our symbol for gas? G. It is a trick question. That is technically wrong. That is not the symbol for hydrogen gas. Must be H2. Okay? That is trickier to understand why that is. Sorry, I spit on the screen. It's bothering me. Okay? How do we know hydrogen should be written as H2?
because there's 2 hydrogens in that first one that we didn't account for.
So that's one option, is going back and trying to say, do things balance out? Unfortunately, that doesn't work because I could have just as easily placed the 2 out in front and done the same thing that you're suggesting. Okay? But that drastically changes the meaning behind this. 2H in front says I end up with 2 hydrogens. H2 says I end up with 1 molecule. that's drastically different. In this case, it must be H2. I end up with one molecule. Right? How do I know hydrogen should come in as a molecule and not as an atom?
Gas.
It's diatomic. What the hell does that mean? Di,
There's two
two, atomic,
atoms.
atoms. Hydrogen is diatomic, meaning two atoms. There we go. How did you know it was diatomic? You memorized it. There are certain elements that when they are in their elemental state, when we reference them, they must always be written as diatomic elements. Okay? You are responsible for knowing that. Hydrogen is one of them. Okay? So more stuff for you to go through and memorize. Okay? There are 7 diatomic elements. Okay? Hydrogen, nitrogen, oxygen, fluorine. Then our halogens, chlorine, bromine, iodine. Okay? You're responsible for knowing those 7. So that when you see any one of those elements all by themselves, okay, or we say chlorine, you know it must be Cl2. What if I only want to refer to a chlorine atom? How might I reference that? But a Cl2 is not a single chlorine atom. That's 2 chlorine atoms making a molecule.
Could you use that with the halogen for it?
Halogen's the name of the group, so no. And for those of you wondering, perhaps you're wondering because didn't I literally just tell you how to refer to it?
Memorize.
No, it was the two.
Name what is in that black box. So Cl usually freaks people out because you're now spelling everything out. So it's like if you were going to communicate, say, hey, M-I-K-E. No, doesn't work that way. You can't do that. Okay, we have to name it by what it is. Okay, so one option was calling it chlorine. No, if you call it chlorine, you're saying Cl2. Okay, so you can't call what is in the black box chlorine anymore. How do I name what is in that black box? It's really simple, and yes, I did literally tell you the answer.
Is it halogen? Wait, what?
Halogen is the name of the family that chlorine is in, so that doesn't work. Like, seriously? You really told me? Yeah. How many atoms are in the black box? 1. So we could call that an atom, right? Which atom is it? Chlorine. How do I name what is in the black box? Ta-da! Okay. If I want you to refer to a chlorine atom, you better say chlorine atom. That's it. That's the only time we know we're looking at a single chlorine atom. Any other time we use the word chlorine, Cl2. Okay? Amazing. All we have to do is add a word, and it all of a sudden, changes the meaning. Okay? It's all Greg's fault. Okay? So how do we know which elements are our diatomic species? There's a couple different devices that you could use to memorize these. Nitrogen, oxygen, fluorine, chlorine, bromine, iodine. That looks kind of like what number? 7, which is kind of important because there's 7 nonmetals. Are there 7 things boxed in right now? One, 2, 3, 4, 5, 6. Dang it, there's not 7, so this device must be wrong, except it's now a red flag. There's supposed to be 7. I forgot one, hydrogen. If you've memorized the 7, you now get a hint that you got to remember the hydrogen. Okay? It's getting colder outside. If we were, say, up north, we're supposed to get a whole bunch of snow, right? Okay? And if you had like a lake, it would freeze over, and what could we do on top of that frozen lake? Okay, we could ice skate. But ice skating's boring because you just dance around by yourself. Okay? What if you got a whole bunch... I'm not making judgments. I know it sounded like a judgment. I'm not trying to judge. Okay? Could you get a bunch of people together to ice skate and do something? Like play hockey. You mean with a hockey stick and a puck? There it is. Also a hint for your diatomics. All you got to remember is that you can use a hockey stick and a puck. There you go. Okay? Those two devices are the most common ones that I have heard since coming here, okay, or coming to this institution. Outside of that, no one ever actually referenced it because I hadn't taught Gen Chem for a while. Okay? The one that I remember all the way back from high school, have no fear of ice cold beer. Have begins with hydrogen. No nitrogen. Fear fluorine of oxygen. You can use the, is that, I don't think that's a mnemonic. Is that a mnemonic? That's considered a mnemonic. There you go. You could use that mnemonic to memorize them. So anytime we reference those elements, you have to know that unless I use the word atom, I'm referring to them in their diatomic state. And you have to specify it as diatomic. Okay? Kind of makes sense? Was a question?
You could also remember, because it kind of looks like a gun that's firing a bullet a little bit, slowly loaded, but...
Yeah, you got a gun and a bullet, sort of. I'm fine with that. Anything you do to memorize that, I'm okay with.
This is only one mnemonic you can create.
Yeah. Yeah? Is that another question, James? No?
No.
Okay. So we good? Cool. So some simplifications. If I asked you to write that out, would you get kind of mildly irritated at me?
Yes.
Yeah, why?
Because it's long and complicated.
It's long and complicated. If you tried to enter that into the calculator, that would probably also be equally frustrating. Is there a shortcut? We could just go 4 to the 6th. Okay? So mathematics created a system that allowed us to do repeated multiplications with our exponents. That's kind of neat. Okay? So what we've got are exponents. The common ones that we see, or common terms associated with these, are squared and cubed. How do you measure the area of a square? Length times width, which would mean, if we did this in centimeters, the centimeters times a centimeter would be a centimeter squared. We're referencing the exponent. If it's cubed, how do you measure the area of a cube? Length times width times height, centimeter times centimeter times centimeter. I don't know why I picked centi. And we'd get centimeter to the 3rd power, or cubed. Okay? So we will be using exponents fairly frequently. If you have to move through Gen Chem a lot more, we'll see them a lot more. But right now it's kind of soft. Okay? We just see them a little bit. Okay? We can use our powers of 10 to represent very large numbers. Okay? So for instance, 1,000,000, we can drop down to being 1 times 10 to the 6th. Okay? And it simplifies the amount of work we have to do. It also helps our puny human brains sort of represent those numbers a little bit better. Because remember, we can't deal with numbers larger than 10. Okay? So when we get up to 100, we can convert the number 100 into 1, which makes it really easy to look at and evaluate. We just have to remember we multiplied by 10 to the 2nd. Kind of makes sense? So our powers of 10 just kind of shrink the number down to make it a little bit more manageable to look at. Okay? It does hide some of the meaning, so we do have to kind of remember that meaning kind of internally. Which gets us to scientific notation. If we take a look at those two numbers, those are really big and really small numbers. Okay? There's lots of placeholder zeros. I don't want to have to write out all of those placeholder zeros. I would like to have a notation that would allow me to ignore those placeholder zeros. This is where scientific notation comes in. So I could reference this number as 4.063 because only those digits are significant. The rest of those zeros are not, at least yet, significant. But now my number went from, 400 million to 4. I've lost a lot of meaning there. I have to make sure that meaning is still embedded in it. That's where my power of 10 comes in. Okay? So the power of 10 in this case will end up being 10 to the 8th. 1, 2, 3, 4, 5, 6, 7. Yeah, 10 to the 8th. Okay? And I've got my number. Okay? We could do the same thing with the one underneath. 1.16 times 10 to the 1, 2, 3. Just wanted to make sure I was right. 7. But I can't say 7 anymore. I'm going to have to say negative 7. Why?
Because you're going out this way, so you're bringing it from a decimal point to the regular number. So that's the goal.
Going backwards.
Okay? So I'm hearing all sorts of suggestions here, and I would argue I like Krista's the best. Okay? Typically what we hear referenced is where you're shifting the decimal point to the left or to the right. Okay? The problem with that is when you go from scientific notation into the longhand notation, you end up doing the opposite shift, which means your left and rights change. Okay, so referencing it as a left and right is actually a really bad idea, and you shouldn't reference it as a left and right. Okay, what we should instead do is come up with a system that will always allow us to evaluate this correctly. Okay, so let's take a quick look at some other examples here. What if I wrote 40.63 times 10 to the 7th? Okay, and before anybody calls me out on it. Does the blue number and the black number and the red number all mean the same thing?
No.
Yes.
Yeah, they do. They all mean exactly the same thing. Okay? We went from 7, but here it says 40. So that just means I shift 1 fewer decimal places to get me to the black than I did with the red. So they all mean the same thing. Are they all scientific notation? The black number is scientific notation? No. I completely agree. The black number is not scientific notation, so they can't all be scientific notation. Is the blue one scientific notation?
No.
No. But isn't it doing the same thing, powers of 10? So you're super confident in that no. Why is that not scientific notation?
It's not at the lowest value you can do that.
When we look at scientific notation, your first significant digit has to show up in the ones place. Why? I have no idea. That's the rule. Okay? That's what it means. Okay? So while this is a power of 10 and it holds all the same meaning, it is not technically scientific notation because you aren't matching the pattern. That's it. Okay? So let's take a look at our powers of 10 again. And because I don't think I have the rule set for it, let's just erase all that. We look 4.063 times 10. How many places did I shift the decimal? 8 places. Should it be a positive or a negative? Is the number really big or really small? Really big. If it's really big, what should the sign be? Positive. We moved the other number. It's 1.16 times 10 to the, I shift the decimal 7 places. Is my number really big or really small? Really small, which means negative. All you have to know is big and small. There's no left and right. Okay? And for those of you that wonder about lefts and rights, we find people that confuse left and rights all the time. Okay? Now all you gotta do with is big and small. Okay? Big number, make it a positive power of 10. Small number, make it a negative. If I had to convert the other direction, okay, it's a positive 8, which means my number needs to get bigger or smaller.
Smaller.
It is a positive 8. Should the number get bigger or smaller?
Bigger.
Bigger. So should I shift the decimal this direction? No, because that's now making it smaller. I need to shift the decimal this way. How many places do I shift it? 8 places. And I can get my, I don't know why I'm rewriting it. I would get my number back. Okay? So positive and negative allows us to jump through those hoops without having to deal with this left-right issue. Kind of makes sense? Yes, James.
So is, because it says big or small, but in scientific terms, is there like a set number? So would 1 be considered?
So when I say big and small, what am I referencing? Right? So Krista had the good point when she made her initial statement with reference to 1, and you're making a good point too. It's referencing to 1. I'm not referencing negative numbers. Okay? So when we're talking about this big and small, it's all in reference to 1. They are always positive values that we're interpreting. I can still convert a negative number into scientific notation. The negative in front just gets kind of ignored. I'm looking at converting the absolute value of whatever's in there. Okay? For instance, if we take a look at that top number, and this wouldn't make sense, but we can look at it. If I made that a negative 406 million, okay, what does that change in my scientific notation? You might say, well, isn't that number really small? Okay? When we're going to evaluate that small and large, we're looking at just the value in between. I don't care about the sign out front. Okay? Which means it's going to be 4.063 times 10 to the 8th. But it's a negative value. Okay? So when we're talking about large and small, we're looking at the absolute value of the number and saying, what is its relationship to 1? If that value is larger than 1, my power of 10 is positive. If that value is smaller than 1, so between 0 and 1, it's negative. Does that help you?
Yeah.
Yes?
So when we're still doing that, maybe we still have to include, 1.16 times 10 to the negative 7, we should have to put, whatever we're measuring still, right? Like, we can put meters?
The unit, yeah. Which I did have on there, and then I erased it and didn't put them back.
So we have
Yeah.
to include the
You still have to include the measurement. Decent? Okay. So the rest of this actually has a bunch of text that I copied from the textbook and I don't like, so let's ignore that. Let's go ahead and take a look at some examples here. How many significant figures in this measurement? So the 4, the 6, the 3,
0 in between.
and the 0 in between. Everybody okay with that? 4 sig figs. Okay. That's just what we see up there and what we're interpreting. So now if we just imagine how this was measured. Okay. Someone took a 1,000-meter stick and measured.
But there's no such thing, so they have to go.
Irrelevant. I don't care if there's no such thing. That's what they're using. They measured by thousands. How many sig figs? Why are you saying 6?
Because I'm counting the other 2 zeros behind 3.
Why are those 2 zeros now counted?
That's in the thousands. Every thousands.
Remember, I'm using a 1,000-meter stick, which means I know that that 0 means not 1 through 9. It's not a placeholder anymore. I know that value is not a digit 1 through 9. Because I'm using a 1,000-meter stick, I don't know what those numbers are. So these are all guesses. These are all, well, sort of just truths. We'll just accept it as truth. When I look at that number as it's reported, is it obvious that I have 6 significant digits? No. So I need to come up with a way that when I report this measurement, where those purple zeros are actually significant. I need to change how I present this number to make sure that when someone looks at this, they understand that I have 6 significant digits, not 4. How do I do that?
So if you
What do you got, Joey?
scientific notation,
How do I do it?
do 4.063 to the power of 5.
Okay. If we did to the power of 5, shift the decimal 1, 2, 3, 4, 5, I end up with the number 406300. Are these two numbers the same? No. I like where you're going, Joey. You aren't all the way there. What did you have, Robbie?
I was going to say 4.06300 times 10 to the 8th.
Now I have
It'd be 10 to, it'd still be.
the appropriate number of sig figs. Okay? Each of those numbers is now a significant digit. Okay? So Robbie's suggestion of adding those extra zeros now makes them significant. Where Joey had initially set up, when we multiply this out, we get this number that didn't make those zeros at the end significant. They needed to get listed there for them to be significant. Okay? So that was one of Joey's mistakes. The other mistake is power of 5. I'm changing the meaning. I'm now 406,000, not 406 million. What else needs to change?
It should have been 6.
Should have been
To the 8th.
to the 8th. Now, those zeros there, those last two zeros are significant digits. In the original writing, they weren't significant digits. So I can use scientific notation to present my measurement in such a way that people understand the meaning of those zeros, that they know they are significant versus being placeholders. All right, I'm going to pick on you a little bit, Joey. Are you on board? Okay, because you had the right idea, just not quite there. I wanted to make sure you were good with it. Yeah. Okay, everybody else? Nobody else volunteered, so I honestly don't know. Okay. So, scientific notation can be used in conjunction with significant figures to help bring meaning in, okay? To help bring those zeros in as significant digits instead of placeholders. Yes?
So is it just this example that we have to do the 4.06300? Because isn't it usually you wouldn't have those two zeros, or do you always have to have those two zeros?
Okay. So, and what I believe you're asking is, do we need to include those two zeros from that measurement?
Yeah.
Okay. Well, it depends on what the measurement was. Okay. If I'm asking you to report that number, okay, let's call the number in the blue box, I want that number reported to 6 significant figures,
Oh, okay.
then you dang well better use scientific notation to keep those zeros as significant. Okay? That's when you have to use it. Okay? So it's coming from the measurement that you take. This becomes a challenging thing for you to wrap your head around, because how many measurements do you take in the lecture?
Or wait, in the lecture?
In the lecture, how many measurements do you take?
Not a lot.
You don't take any measurements in the lecture, so you don't get exposed to this issue. Okay? It's only in the lab that you would be taking these measurements. Okay? Where it could show up in the lab is if you went in and used the balance and you were supposed to weigh out approximately 5 grams. So the balance, right? Here's our little balance. There's the screen. There's a little plate there, right? Everybody got that? There's our balance.
Quite a few balances, haven't you? I can just do that on the spot.
Definitely better than what I could come up with.
Our balance reads out 5.002. In fact, let's go ahead and do this. If I tell you to measure out approximately 5 grams, you measure something out on there. There's your little mound of stuff. What do you tell me you weighed out? 5.032. If I say approximately 5 grams, what I'll get students writing down for in that little line with how much did you weigh out, you'll write 5 grams. What did you just do?
Mess up your data for the rest of the experiment.
You deleted all of those significant digits. When it's 3.2, you were like, well, but it said those, so I should write those down. What if you were really, really careful when balancing or when measuring, which arguably, if we say approximately 5 grams, that does not mean measure out 5.00 grams. Okay? It means approximately. Should you be writing 5 grams now?
No, you should write 5.
You should be writing 5.000. Why? Those zeros are significant digits. The same issue is happening as over here. Okay? Except, do we need to use powers of 10? No, because it was already a nice small number. So we don't have to use scientific notation to represent those zeros, but it's the same concept. When you go through to report that measurement, you have to include it with all those significant digits. Even though you think those zeros don't mean anything mathematically, they do. They mean don't use a digit 1 through 9. Okay? When we add it up, we won't see that effect as an obvious effect in our numbers, but it is implied behind the calculation. Kind of, sort of? Okay. So, chapter 2, our metric system. We get a bunch of different, what the textbook refers to as basic units. I'm actually going to call them core units. Okay, you might also hear me reference them. I forgot what I might reference them as. But I'm going to call them core units, okay, because they're the thing that make these things up. Okay? I think we talked about measuring mass, and I said there's that little YouTube video where a guy gets excited about a big silicon ball. Okay? He gets excited about it because the basic unit for mass is not a gram. It's a kilogram. And that big spherical ball that he's playing with is exactly 1 kilogram. Okay? Exactly 1 kilogram. So it's kind of phenomenally neat that someone was able to make exactly 1 kilogram. That's why it's cool. Okay? So when the textbook says that the basic unit is a gram, they're wrong. It's a kilogram. Okay? This is why I switched up and used core unit. We're talking about meters, grams, and liters. Why reference it as a core? Have you heard of another unit involving meters, grams, or liters? Yes, you have. Volunteer one.
Milliliters.
Milliliters. What is the core unit for volume? What have I done? To get the milliliter measurement, I've added a prefix on top of the core unit. Okay? So if we know what the core unit is, all we have to do is do simple prefix adjustments to it to change the measurement system. Okay? So we'll reference the core unit a lot because it is super important to be able to acknowledge it and to see how we can interconvert to these other prefixed units.
What about the time?
So for time, have you heard of milliseconds? What is our core unit? Seconds.
What if you say you can't say hour?
I was waiting for that one. When we go through and look at our length, mass, and volume, those are all done pretty consistently, okay, with this prefix system. Time is not one that has been used with the prefix system super effectively. Okay, we do see it pop up, milliseconds, okay, but if we start going larger than a second, we don't go to kiloseconds. We would jump to minutes. We jump to minutes. And if we go larger than a minute, we go to hours. Okay? So we have a different system, a different base system for time. Okay? Arguably, time is like the American system measurement. Okay? We pick some random values to kind of jump in. They aren't random. There is a larger logic to that system. But when we look at time, we go seconds, minutes, hours, days, and we aren't using a nice core system. Okay? We can still overlay the core system on top of your time units. We can do milliminutes. We can. It just sounds really weird. We wouldn't bother to do it. Okay? But if we're looking at something shorter than seconds, we almost always drop in a prefix to reference them. When we go larger than seconds, we jump to minutes. When we go larger than minutes, we jump to hours. Okay? So you tend to not see the core system used as much with time. Okay? Whoops. Powers of 10 come back again. What we're talking about is memorizing what those prefixes mean as according to the powers of 10. So if I say milliliters, what am I saying? Well, what does milli mean? What does that lowercase m mean? Means 10 to the minus 3. Okay? It's still liters. 1 milliliter is 10 to the minus 3 liters. It literally translates straight out of the language of knowing what those prefixes are. Okay? So you need to now memorize not just that we have powers of 10, but what is the meaning of each of those powers of 10. 10 to the minus 3 means milli. It doesn't mean milliliter, it just means milli. Okay, what is our symbol for milli?
M.
Really?
Capital. No, because those
Lowercase.
lowercase.
Lowercase m. So does capitalization matter?
Yes.
Yes. Okay, so you need to be careful with it. Okay, some people will go through and reference, well, the capitals are all big. Kilo is not big. Kilo is lowercase. So if you go to a bigger number, a lot of them are capitalized, not all of them.
Any particular reason why the K in kilo isn't?
I'm going to bet the K in kilo comes from what the base unit is in mass, which is kilogram. And since that was used as the base unit, that's why it's lowercase. Okay? The prefix system was then overlaid on top of it, and they were like, oh, well, we could overlay that on top of grams, not kilograms, and it makes more sense. Okay? So I think it's an artifact of what we decided was the base unit for mass, and that kind of messed with the prefix system. And instead of going back and changing what our base unit was, we just kind of switched the system as we dealt with here. So I think that's an artifact of that. Okay? So you're responsible for knowing what the prefixes are and what they mean towards our powers of 10. Do you really want to memorize all of them? No. So let's simplify. You have to memorize 3. Kilo, centi, milli. Do you still need to use all of them? Yes. When you go to the homework, I fully expect you to be able to solve things with those other prefixes. You just don't have to have them memorized. You just have to use them. Okay? When it comes to an exam, I expect you to have kilo, centi, and milli memorized. Could I still ask a question about tera?
Yes.
Yes. What would I do to change the question so I could ask about it?
Give us the measure.
I'll give you what tera means. Okay? Feel free to look at exam 1, the front page. You'll see that there's a bunch of information given to you for every exam. You'll find some of those weird prefixes also included on the exam. Okay? Just because it's on the exam doesn't mean you'll use it, though, because I would bet none of you used the first section of information on exam 1. Okay? But you will start needing to reference it. This is why I recommend you tear that first page off. Okay? So, now we can put it all together. If I take a look at scientific notation for that first number, my scientific notation becomes 1.2 times 10 to the 1, 2, 3 places. That number is larger than 1, so it's a positive 3. And this was meters. What is my new number, or my number and new unit? 1.2. Well, what is 10 to the 3?
Milli?
I just told you to memorize these. How come you didn't memorize them?
Oh, 10 to the 3 is kilo.
10 to the 3 is kilo. That was your opportunity to chime in, Haley, that you'd written them all down. It's okay. And I end up with kilometer. There it is. 10 to the 3rd gets folded in to the meters. Do you guys want practice with those?
Yeah.
Do it.
Is that a capital
That is a lowercase k. Sorry, making a mistake because what you are writing down has already been given to you. You have it in the slides. What you should be writing down when I ask you to solve something is the solve, not the question. Okay? If you want, I can even make sure I go through and make sure the slide numbers actually show up on each page, so you could write slide number and reference it back to the work that you're showing. Writing the question is a waste of your time. Okay? When we go through to solve this, that second one, how many places did I shift the decimal? 2 places, so this needs to be a 2. Is that number large or small? So it needs to be negative. 10 to the negative 2 is, Haley? Centi. And I get 1.2 centiseconds. Okay? I move to the next one. I shift the decimal place.
-2.
2 locations. Okay, it's a small number, so negative 2. 10 to the negative 2 is centi, and I get centiliters. The last one, I've shifted the decimal place. 3 locations, large or small? Small, and I end up with milligrams. Okay? This is one way that we can deal with converting into these prefix units. We recognize the meaning of the power of 10, and we can convert those across. This works really well when we're going from a base system into the prefix system. If we try and go the other direction, it can get a little bit dicey, okay? And so we'll have to create a different mechanism for solving those, okay? So if we go through and take a look at some of these, we can look at kind of the English language, the mathematical language, and then what I would argue the useful mathematical language. In English, there are 1,000 meters in 1 kilometer, okay? And you might make the argument, well, how did you get 1,000? That's not a power of 10. And I'll accept that. We're saying there are 10 to the 3 meters in 1 kilometer, because kilo means 10 to the third. There it is. Okay? If we go through and look at the mathematics, we could then change some of that English language around. We can drop articles and verb, subject and verb. The in becomes the equals, and we now have a mathematical language for this. We can even adjust it in kilometer. We can make approximations or simplifications, and we end up with km. We go 1 km equals 1,000 meters. Okay, notice with the 1,000, I multiplied it out. Why would I multiply it out? How many of you like powers of 10? Ouch. Guess what? You're not alone. Most people don't like powers of 10. So when we created the system and tried to deal with these common things, instead of memorizing powers of 10, we multiplied it out to get 1,000. Okay? This was done by people long before you, so that when you were taught and trained how to deal with these memorizations or these conversions, you were asked to memorize 1,000 meters. Okay? So let's look at the people that trained you. Why did they write 1,000 and not 10 to the third?
Because they like the shortness of it.
10 to the third is longer than 1,000.
Oh, I thought we were talking about kilometer.
All we're comparing is 10 to the third and 1,000. If we say we're inherently lazy, 10 to the third is shorter than 1,000. Not by a lot, but it is. Why would we reference 1,000 and not 10 to the third?
I mean, it's the same answer. It's kind of like if you say 60 seconds versus a minute. 60 seconds is more specific in my mind. Like you do.
So the issue with that example is you're shifting to a different base system. Here we've got prefixes, and so I think I understand where you're going with that, but unfortunately it's not going to quite line up. Okay, I actually gave you the answer to this already. How many of you like powers of 10? Nobody raises their hand. Guess what happened 1,000 years ago? Nobody liked powers of 10 then either. Okay, so they went through and said, well, powers of 10, 10 to the third is 1,000. I can deal with 1,000 mathematically or numerically a little bit easier than dealing with this weird exponent thing, because I could get confused by what's happening up there. Okay, Well, 1,000 years ago, what did they not have that you do have? You have a freaking calculator. And what does the calculator do? Powers a 10 pretty amazingly well. You don't have to memorize that 10 to the third is 1,000 because what do you have in your pocket? A calculator. Okay? There's internet memes out there. Your math teacher is like, you'll never have a calculator with you for the rest of your life. You need to go through and know how to do these things. You're wrong. I have a calculator with me for the rest of my life. It's in my phone. Okay? Use the power of the calculator to cut down on the amount of memorization you have to do. I don't have to memorize that converts out to 1,000. Okay? I can keep it as the power of 10. Okay? This may seem very subtle and simple, but there's lots of little memorization things that you have probably already done that you don't have to do, and you have a higher frequency of misimplementing it because you've incorrectly memorized it. Okay? If we've got the ability to use the calculator, use the calculator. Okay? So, the last step, how do I convert this into something useful? What if I divide this side by kilometers, by 1 kilometer? What would I have to do? I have to divide on both sides, right? What is 1 kilometer over 1 kilometer? 1. Can't simplify the other side, 10 to the third meters, 1 kilometer. And now we have a useful format. This purple box is awesome because that purple box equals 1. And when I multiply anything by 1, what happens? You get itself. So I can now use that fraction in virtually any mathematical system I want. I'm like, well, that's not all that useful. How do I convert? Okay. Times 10 to the negative 3. Super common answer. Is that correct? No. For a couple reasons. What happened to the unit?
It turned into a negative 3.
So the 3 is a number and the unit is a letter. The letters will never change into numbers. That doesn't happen.
It changed from kilometer
Into meters. What about in that work on the left-hand side of that equals happened to the kilometers? I haven't done anything to the kilometers, which means if I solve this,
You're still going with kilometers.
I still get kilometers. Is that what I wanted?
No.
No. Okay? So let's deal with that and push this out a little bit further. Let's actually include the units in our calculation because the units are important. We want kilometers showing up in the denominator. Why? So the unit can cancel out. What unit do I want to end with? Meters. So I could put meters in the numerator. Now I know the units that need to go through to do this conversion. Now what do I need? I need the numbers that I would put in here. Thankfully, Robbie gave us a number, 10 to the negative 3, and we said times 10 to the negative 3. So now all we do is solve and still wrong. Multiplying by a number in a conversion system is a horrible process to go through because you can make the very simple mistake of putting the number in the wrong location, be it a numerator or a denominator. Okay? And this may seem like I'm picking on Robbie. I'm not. I'm picking on all of you because you're all going to make the exact same mistake. I've made the exact same mistake. All I have to do is multiply by this. No, write out the freaking unit work to allow you to see where to place the numbers. And we go through and do that, what happens? That needs to be a positive 3. Now when I go through and solve, everything works perfectly. The fraction that I've established from that equality tells me where to place the numbers, when I track the units appropriately. If I don't track the units, I can place the number in the wrong spot. Okay? That massively changes the end result. Okay? So when we talked about numbers early on with measurements, I said when we look at a measurement, it's a number and a unit. Okay? And I apologize, Robbie. I needed you to do that, so I really do appreciate it. Okay? When Robbie said multiply by 10 to the minus 3, that's inherently wrong because all you're multiplying by is a number. Numbers are meaningless unless they have a unit. And as soon as we brought in the units, we found out that the number that he memorized to use was not right. The unit allows you to see that mistake. Without the unit, you have no context by which to base if your answer is correct or not. Okay? All of this English that gets converted into the mathematics, that gets converted into a useful system, is all behind all of those conversions. And when you've memorized your powers of tens and convertings, you may have heard the whole King Charlie shuttled chocolate through pineapples, something like that, Henry, whatever it is. Okay? That was a huge disservice to you with dealing with the powers of 10. Ultimately, all that got you to do was memorize the prefix and the number, but lose all context of the meaning. Okay? And it can potentially even allow you to, you just shift the decimal left or right. No, you've lost context of the meaning. And in an algorithmic system, if you do that calculation again and again and again, you've shortcutted the amount of work. And that's fantastic in an algorithmic system. Do you know what does a really good job of solving algorithms? A calculator or a computer. So if we train you to solve algorithms, we have trained you to not have a job the rest of your life. Okay? What we need to train you to do is not do algorithmic solving, but understand the process by which these things build. Because what can you do once you understand the process? You can build the algorithm that then keeps you in a job. Okay? That's what we're working towards. So you may see shortcuts and all sorts of fun things like that out there. You're welcome to learn and use those if you want. All you are doing is preventing yourself from getting a job in the future. Okay? So you're literally setting yourself up to pay somebody to teach you how to not have a job. Okay? You are paying somebody to take away your job. That's not a good philosophy. Okay? So what we want is that process behind it. We need to be able to do those interpretive steps. We need to understand the English so that we can convert it into a mathematical system that we can then use to set up conversions and unit systems. Okay? It's pretty phenomenally cool. And I hate to admit it, it's all rooted back in the English language. I don't really hate to admit it. I accept it. Okay? So we have to be able to understand at all of those levels. Okay? So, some mathematical manipulations. The negative sign is always something that trips people up. Okay? If you're having a hard time with dealing with all those conversion things that we just threw out there, you may want to take a mental break and just kind of not pay attention to this for a second. The negative sign means do the opposite. That's it. Okay? So if I go through and take a look at the calculation where it's a positive, well, that means don't do the opposite. Just do it as is. So I do 10 to the second, which is 100. Where was that calculation performed? Or what the hell does that mean? Where was the calculation performed? In the numerator. Is there a denominator?
There's one.
Yes, there is. There's a 1. Every number you've ever seen is a fraction. There's always a numerator and a denominator, except the denominator is usually 1, so we ignore it. Okay, fractions are everywhere. We need to acknowledge that and use that. When we go through and look at the -1, what's happening? That negative means run the calculation in the opposite location. Do the opposite. Where's the calculation currently being shown to run? In the numerator, which means where should it run? Those are mathematically identical. Okay? Amazing. Simple, tiny tweak, and allows you to simplify and adjust where you run your calculation, numerator, denominator. You don't like that, that's fine. Okay, why is it fine? You have a hard time with minus signs. You have a hard time with powers of 10. What does not have a hard time with minus signs and powers of 10? Your calculator. You can use the calculator to run the calculation for you. Okay? Where it can become problematic is if you have to scale a bunch of these kind of calculations together, you increase the odds of making a mistake and entering it into the calculator. The calculator's not going to make a mistake, you will. If you can simplify through some of these kind of mental gymnastics, the stuff that you enter into the calculator, the better off you can be. Okay? The minus sign is a nasty thing to worry about, okay? And it comes back to why we memorized certain things. Do this. Okay? If I ask for the amount of centimeters in a meter, what do you tell me? Cool, since you're looking at notes, that's awesome. Don't answer the question. You're going to do it right. You're going to deal with what does centi mean, powers of 10, that's awesome, fantastic. If for whatever reason you thought the word 100, you were wrong, what you did, okay, is you took the power of 10 conversion system and you said you didn't like powers of 10s and negative numbers, and what did you do? You ran the calculation in the opposite location. 10 to the minus 2 in the opposite location would be? Some people will memorize 100 centimeters in a meter. It's not what I told you to memorize. Okay, why? Because you will goof where you place your power, your number. Okay? At some point, you will screw up and place it with the wrong unit. With the process that I've told you to deal with memorizing, you can't make that mistake because of how we set up our conversions, which we will see in a little while. And by a little while, next week. Okay? So we'll jump back to Chapter 3 to finish up some stuff in Chapter 3. We've got our qualitative and quantitative observations. We could use those to monitor our physical and chemical changes. Okay? As we learned in the lab, it can be difficult to qualify what is a physical versus a chemical property. Okay? Particularly really early in the semester. Because a chemical property has to do with making or breaking a chemical bond. How many chemical bonds can you see? Rhymes with hero. There's no word that rhymes with hero. Zero. There are 0 chemical bonds that you can see. So when we're talking about chemical and physical properties, we're asking you to look at what you can see and extrapolate to what that means about the chemical properties. That's a difficult thing to do very early in the semester, because what is your concept of a chemical bond? You don't have one, because this is your first chemistry class. So it becomes difficult to process. Okay? Where this is really going to come in is with our chemical and physical changes. Okay? Our physical changes, we're changing something about what we see, but it doesn't change the chemical bonds. Done at 15? Good. Our evidence for chemical reactions. Notice that it has a red title on it. Why would it have a red title on it? Does this slide look familiar to anybody? Everybody should be saying yes, because I asked you to watch a Play Pause It video that has this slide in it. The red slide means you've already seen it. Okay? So you understand these things, or at least have a concept of chemical and physical changes, right? So these all represent what? Chemical or physical changes?
Red represents physical.
All of these. All represent
Chemical.
chemical changes. If I take a block of ice and I hold it into my hand, what happens?
Melts.
It melts. Did I change the phase? Yes, I went from a solid to a liquid. That's rule 1, a change in phase. We just said that means a chemical change. So when I hold on to that block of ice and hold it in my hand, that's a chemical change? Why not?
It can go back to its original state.
Okay? So we could reference the reversibility. It can go back to its original state when I remove the heat. Okay? The big caveat with this first one, it's not heat induced. Okay? When I take that block of ice out and hold it in my hand, what's the heat I'm supplying? My hand and the room that I put it into. That's why it's melting. Okay? I've added the heat to cause the phase change. If I take two liquids and I mix them, I haven't added any heat. If I see a gas all of a sudden form, where did the energy come from to transition from the liquid to the gas? From one of the chemicals. That's why it's a chemical change. Okay? So when we're looking at those phase changes, what we have to reference is be aware of that you're not looking at things that you have caused to happen. The chemicals have to supply that energy. Permanent color change. Has anybody added red food dye to cake frosting? Yeah, and you stir it in, what happens?
Changes to red.
White cake frosting changes to red. Is that reversible?
Yes.
Yes, you go the opposite way.
Yes.
If you go in the perfect opposite direction, yes, it is reversible. Okay? Which is insanely crazy to observe. There's actually videos that show it. It actually happens. It's kind of neat. Okay? It's not easy to do because you have to go in the exact opposite direction. Okay? And when you go through and mix in the cake frosting, are you just going in a nice perfect circle? No, you're usually going all which ways, which makes it difficult to replicate going reversed. Okay? So a permanent color change is not a dilution in color. Okay? So what we could do would be look at, say something like that. We have two clear colorless solutions. I mix them, and what do I see? A yellow. Where the hell did the yellow come from? Right? Chemical reaction. Okay? Last one, an energy change is observed. There's all sorts of different forms of energy. The most obvious one is heat. Okay? If I mix two chemicals in the solution, it gets hot. Why is it getting hot?
Chemical change.
Okay? The chemicals are releasing energy out, which is now being absorbed by my hand. That's why it's getting hot. If it gets cold, the chemicals are absorbing energy from their atmosphere, okay, or their surroundings. Okay, so we can look at energy changes as well to represent our chemical reactions. So, chemical or physical, notice this one isn't red. Melting ice.
Physical.
Dissolving sugar.
Physical.
Burning wood. Okay? So you're suggesting physical. What happens to the wood when I burn it?
Is it charcoal?
Turns into charcoal. Okay? If I stop adding heat, does the wood reform? No. Okay? So we can think about that reversibility. It's not reversible. Okay? If we add the heat and it starts to burn, okay, and we stop adding heat, do I get the mass back? Do I get the same weight of the material? No. What happened to all that mass? Didn't just go away.
Turn to gas.
Turned into a gas. What gas?
Carbon.
CO2. This is one of the reasons why we have a massive issue with greenhouse gases of carbon dioxide. All of the combustion, all of the burning of materials that we do is generating CO2. Okay, that CO2 goes out into the air. Okay? So we've changed the chemical composition. We've generated a new phase, burning wood. Okay? Mixing red food dye with white cake frosting. Physical, we just addressed that one. So now we got two interesting ones at the bottom, or the dissolving salt and the one at the bottom. What's happening in the one at the bottom?
Changing color.
The
Yeah, we're changing color. Okay, which would suggest? Well, it depends, right? What's causing the change? I shined a UV light on this crystal. When I shine the UV light on the crystal, it changes color. When I remove the UV light, what happens?
It goes back.
It goes back. Physical, because?
You added
Okay. We could go, we've added the energy. That's not a bad idea. It's reversible. It's actually chemical. Okay. How do we know it's chemical?
Is there like leftover?
Nothing about what we physically observe allows us to know it's chemical. Nothing. This is why differentiating chemical and physical changes is a challenging thing to do. Okay? Dissolving salt,
That's chemical.
that's chemical. Why? What is salt? Describe salt to me. A white solid. What is sugar? A white solid. When I dissolve sugar, do I end up with the same looking thing as when I dissolve salt? Yeah, it's a clear solution, right? Okay. Dissolving sugar is absolutely physical. Dissolving salt, it is chemical. You're breaking a chemical bond. How would you know that based off your observation? You wouldn't.
You'd have to heat it up, wouldn't you?
Okay? You would have to try and do some other test to figure that out. Right? When we talk about chemical and physical, it is presented as black and white. There's a giant freaking rainbow up there for a reason. Is it black and white? No, it's a continuous spectrum. Depending on where we fall on that spectrum, we can be more chemical or more physical. Dissolving salt happens to fall pretty much dead in the middle between those two, and it's really entertaining to look at the debate that you can find online with that question. It is absolutely a chemical change because you are breaking a bond. Okay? With that, we have to end.